Hello everyone, good morning. I guess the rest of you still in the lab, so never mind. We will start the sessions and your friends can follow with these videos later on, right? So the attendance link have been posted in the chat box, so you can take your attendance there and we will start now. Right. So today's topic would be on the FEA software. Okay, so we try to understand what is actually happening behind an FEA software. Okay, so as we have discussed previously, we say that in this course we intend to understand what are the concept being used, okay, behind FEA software, right? But before we dive too into the finite element methods, okay, I think it's good that we just run through some FEA software. I can run and see what actually occurs behind it, so that you will appreciate more when it comes to the finite element methods concept later on, right? So the goals of these lessons today is to meet the course outcome number 5, which is to ability to solve the engineering problem with finite element methods numerical tools, right? So again, as you can see, these lessons or this chapter may not directly allows you to solve to solve a problem directly, but then throughout the course you will fine-tune your skills from there onwards. Okay, so today's lesson only give you some ideas, okay, how it works, okay, how you can run a basic finite element analysis, right? So as we have seen previously in the slides, okay, we say that in a finite element methods process, okay, we have a physical problem, we form mathematical models, okay, then we start with our finite element solutions, which includes the formations of finite elements mesh, okay, then we represent other loadings and other things, right, before we can run our analysis. So as you can see in this CAD model, all right, so this is just a clip, all right, with two holes, okay, screw holes, okay, which will be used, let's say, for mounting camera, right? So you may have this clip, all right, to mount a camera. So this screw hole will be screwed on this camera mounting, all right, so that you can clip it on most of the things, like maybe some rods or whatever it is, right? So now, as you can see, right, so from this model itself, if we intend to analyze, okay, so the main critical part may occurs on these sections, right? From our experience, that when we clip, right, when there is a weight, okay, pulling downwards, okay, therefore we have some stress, okay, occur at this particular joint, right? So this is the ideas of why we need to run some analysis and to know whether the thickness or whatever it is it sufficient to actually hold the weight of a camera, right? So this camera itself is your physical problem. You may want to define the weight of your camera, okay, let's say it's a DSLR camera, let's with maybe half kilogram, okay, 500 grams. So from there onwards you will convert into newtons and apply the loads accordingly to your problem or the physical the CAD model itself, right? The idea is that when we intend to run it in a finite element analysis software, we would want to convert the physical problem into a finite element model. We have this word finite element model. It's not a CAD model, right? So this is a CAD model, right? Drawn in Fusion 360, right? So you can access Fusion 360s from your home or maybe through the UMS Smart Desk, right? The problem is that when we intend to translate this problem, this CAD model, into an analysis, you may choose, okay, what type of finite elements that you want to represent this model. Okay, the basic element is the line elements, then slowly there is a shell type of elements, and from there onwards we can extrude the shells into a solid elements like cube, right? So this is how it would looks like. Okay, you can represent this model using lines element, okay, 1 element, 2 element, 3 elements, 4 elements, and the 5th element, right? So this is how you can represent your elements, right? These models into a line element. Okay, you can also represent them using a shell element. Okay, so you use a shell, okay, to represent this particular thickness. Okay? So this side, okay, have 1 shell, the second, third, fourth, fifth. All right, so I purposely draw in this way so that you can see there is different surface or shells actually going through, okay, touching each other over here, right? So this is how you can translate it, okay? Or the best one, okay, you may want to sometimes is using a solid, meaning to say you may have this physical model or solid models into cubes. Okay, so you may have this running as a cube itself, right? So you can divide them into cubes, okay, so to form a 3D models, right? So this is how you can convert a physical problem into different finite element models, okay, depending on your selections of finite elements. Okay, you can have line elements, okay, shell elements, as well as a solid type of elements. Okay, besides that, you can also decide whether in a finite element analysis software itself, you may want to simplify your analysis by identifying a surface where there is a symmetry line, right? You may have a symmetry lines as shown. Okay, you may say you have this symmetry surfaces, okay, as shown, right? So this is the symmetry surface. Okay, then beside that, okay, you may also want to identify a case where you may have an axis symmetries. Okay, for example, if it is a circular problem, and you may identify that they are symmetry along an axis. Okay, so meaning to say you can simplify it as a plane problem, okay, which is axis symmetry. Right, so this is how you can simplify your finite element models into different type of finite element models later on. Okay, so first thing first is, as we have said previously, try to download Lisa FEA, right? So go to Google's, okay, and type Lisa FEA, right, and type search. If you only type Lisa, then you will come up with this Lisa, right? So make sure you get the right software, okay, and it is free to use up to 1300 nodes limit, okay, that you will know later on, right? Now come to the general steps of the FEM. As we have seen this previously, there are basically around 8 steps, okay, to solve for finite element models. Okay, we start with step 1, step 2, okay, which is related to the element types and the discretizations of the elements into a mesh itself, right? Then from there you will have to select a displacement functions, okay, associate with the elements. Okay, this part you may not see it directly in the in the in the software itself, okay, but when you select, you may say that there is a linear type, quadratic type, okay, which you will see in the examples later on, right? So you can start the Lisa FEA, okay, so this is the interface of a Lisa FEA, okay, so just download and try it on, right? So once you have downloaded it, right, the interface is quite straightforward, okay, you just have to create wait for a while. Hello, I have a class now, right? So so this is the interface of your FEA software, okay, where you can select different type of, maybe a knot, okay, rectangulars or a cube. You can form your own 3D models over here, okay. You just play around with it. This is the graphical part, okay, where you just use this part to create, okay, these few tools to create your models, okay, just like a CAD model, right? So once you have create this one, okay, at the same time you can select different faces and so on, extrude it and so on, right? So once you have created your model, okay, then you can also display it with maybe different type of way of displaying this, okay, like maybe transparent or maybe only showing the outlines and so on, okay. So you can play around with that, okay. The easiest way is just download and just started to click, right? So that is the easiest way to play around, right? I guess now you don't need a specific classes, okay, to do that. If you need, then you let me know later on, right? So basically you just play around with this toolbar, right? Click few, okay, few points, connect them, okay, then extrude, you get your model. All right, so play around with this, okay. You can create nodes, okay, and so on, right? Then after you create your model, okay, after you create the model, you can also want to create your elements, right? So basically when you use this Lisa, I would say when you try to use this Lisa FEA, okay, whatever you draw in the software, okay, is represent an element, okay. You may want to use the auto mesh 2D, okay, to create the different type of meshes, okay. Then you may also select what type of elements you want to represent, okay. Either this line type, okay, quadratic type, it means the shell type surface, or the solid surface, okay. So you can see that these elements actually with 2, 3, try 3, try 6 and so on, there is a meaning behind them, okay, which you will slowly see when you come to the concept of FEA later on, okay. But for today's, the purpose is just to introduce you with the interface of the software, right? Just to play around and get started. That's it, right? Whichever you select, no problem for time being, right? So once you have created, basically you can see that it creates several code, right? You may see not ID number 1, okay, then there is a coordinates, okay, not ID number 2, there is a coordinates and so on, right? So this is how you can create several nodes at a specific locations, okay. You just create different nodes, okay, if you want, right? Otherwise you can also use the auto mesh to helps you to mesh the whole surface, so that eventually you get this triangle. You may not want to draw all this point or triangle on your own, right? So the software itself will have these functions called auto mesh or mesh features to helps you to create all these triangular elements, okay, triangular elements, right? So we call that as auto mesh features. So in the auto mesh features, again, you may have like maximum elements. Let's say you want to have 10 elements, okay, in a row, right? Then how it should mesh, okay, whether it's gradually or very aggressive, okay, or then you have also have this quadratic elements, okay, which we will mention it later on, okay, quadratic elements, okay, with a mid-so nodes, right? So there is a features where you start to take control of what type of elements you going to use in your finite element analysis, right? So this is how you can do some kind of a mesh control, right? So in this mesh control itself, okay, let's say you use the normal type, okay, you can always change the element shapes, right? Or maybe when you want, okay, you can have this mid-so, okay, this is where when you take this quadratic elements, okay, with a mid side node, okay, so within this solid element itself, you can see that every single edges there is a mid node in between it, right? So we call this as a quadratic type, right? Then also you may have a different kind of others tools, like you can mirror your mesh, okay, you can mirror them, okay, so that you may want to draw only this surface, okay, you mesh this up and then you copy or mirror it to the other surface, right? So this is how you can do it, right? Then also within the software itself, you may have a tools like you can refine, okay, the mesh, okay, from very large to a very small size, okay. This is the general ideas of what the software at the beginning they will do. It's behave like a CAD software, but then it add another layer of meshing, okay, where they will start to embed different type of elements within it, right? So in a FEA software, okay, if you are not using the type of designer software, okay, then usually those FEA software like Lisa itself, they have a set of unit system, okay. These unit systems is where you must make sure you are consistent when you're assigning the numbers, okay. What it means is that if you, let's say you are using MMGS, okay, MMGS means all the length is defined using millimeter, all the mass is defined in gram, okay, all the force is defined by micronewton, and time defined in second, right? So you make sure when you key in your numbers, okay, into your FEA software, stick to a single unit system, okay. You can choose MMGS, FPS, IPS, SI, and so on, but then it must be consistent within it, okay. The reason that you need to make sure they are consistent is that the equation behind the software itself, they just do a multiplication or additions by itself, okay. They don't know what unit they are playing around, right? So what you put in, they will not convert, okay. They just plug your numbers into the equations and compute, right? So therefore this is very important. So once you use a consistent unit system, then what you interpret later on, it will give you some meaning, right? For example, if you are using MMGS system, okay, later on if you run the results and the result is a kind of stress result, okay, so that stress will have a number, and that numbers will tells you it is with a unit of Pascal, okay. Or if you want to define the density of a material, then you have to define them into gram per millimeter cube. You have to convert it manually on your own and key in that value into your FEA software, right? So maintain them, and then that numbers will be interpretable or meaningful for you later on. All right, or else if you keep interchange like meter, sometimes meter, sometimes gram, okay, sometimes kg per meter cube, right? Then what you interpret later on in the stress, you may not get Pascal, you may get maybe 100 Pascal and so on. So that's why maintaining a consistent unit system is very important, right? Okay, so like Lisa itself, okay, this is how it would looks like for the nodes coordinate. Okay, so minus 20, 50, right? So in the CAD software as well as in the FEA software itself, they don't define the unit for you. So this can be meter, can be millimeter, can be micrometer, and so on. That's why being consistent in using the unit is very important. Okay, so if you are using a consistent unit system, then whatever it is, okay, it is interpretable, right? So you may have meter squares, okay, you may get speeds, okay, and so on, right? So they must be consistent so that you can interpret it later on, right? So next is the before I forget, this is the displacement functions, right? And these displacement functions refer to the equations behind the element, right? And that displacement functions differs, okay, in between like linear type or quadratic type. Remember, I showed you there is a linear type, there is a quadratic type, okay, of elements. So the equations associated with all these elements is different, okay, and how they calculate is slightly different, right? So that is where behind the software you do the meshing, okay, you do the auto mesh functions. They actually discretize your elements. You also select the element type, whether linear type, shell, line, and so on, okay. Then when you assign whether it's linear or quadratic, then the software itself behind it, they actually select the proper displacement functions to be used, okay, in your elements, okay, or final element itself, okay. Next would be in the solver part, okay. So what the solver part is that after we have established these parameters, when you click the button solve, right, what the software did or do behind it is that they will start to define the stress displacement relationship, form the matrix, solve them simultaneously, assign all these boundary conditions, and and solve it, right? So that is where you need additional inputs to define the so-called boundary condition for it, right? So the first thing, very important part, is to assign the material property, right? So there is a material database, okay, inside it, but if you click the material database itself in the Lisa, it's empty, right? So you have to key in this value by yourself, okay. How to key in this value on your own? Again, you have to check Young modulus, Poisson ratio, density, thermal expansions, and so on, right? So if you, let's say you Google, okay, you found a material like a steel, okay, and the steel's Young modulus, let's say, is 200 megapascal, okay, 200 megapascal, okay. If you are using a MGS system, 200 megapascal, but then Young modulus is in terms of Pascal, right? So you have to convert that mega into 10 power of 6. So eventually what you need to put in is 200 E09, okay, 200 E09, okay, you can type 200 E09. Basically this refers to 200 times 10 to a power of 9, right? So this is how you should key in your material property, right? And this material property only useful for a unit system called MMGS or SI unit, right? So you should make them consistent. Okay, this is why the unit system is very important. Then if you are using MMGS system, okay, then you have to refer to the density. Okay, density must be defined in gram per millimeter cube, right? So convert them and put in the proper value over here. Okay, this is where the unit system is very important. All right, so once you have assigned your material, next would be on the loads and constraints. So I believe this one is more on like a free body diagram. Okay, you can assign a fixed support. Okay, you may put in how much displacement you want. Okay, at a certain point you have force or pressure or maybe gravity acting on your model, right? So you have to assign it accordingly, right? So once you have assigned it, then you also need to define what type of analysis you may want to run. Okay, for time being, or for this course, we will focus more on a static analysis. Okay, static analysis or structural analysis. Right, so you can start with the static analysis. You just click static analysis. Right, then what you need is, in order to assign the load, okay, you just select any point or any surface. Okay, right click it. Okay, then you select new loads or constraint, then you select the list of the boundary condition that you may want to assign in. Okay, then from there put in your values. Again, this value must according to the unit system, right? Unit system, right? So you can also use you can try use control and use your mouse selections. Okay, select it so that you can select numbers of nodes or surface. Okay, different type of surface. Okay, then you can assign it as a whole, right? Next would be on the analysis type, right? So once you have assigned all these things, when you are almost going to solve your problem, what you need to do is you just have to double click this analysis or right click. All right, then it will prompt you with this box. Okay, and it will ask you what type of analysis you intend to solve, right? So as we have mentioned previously, we intend to solve a static problem. So if you are using 3D elements, okay, then you use 3D. If you are using 2D elements, then you have to choose 2D. Or if you are solving for axis symmetry problem, then you have to select axis symmetry. Then you have the list of analysis that the software can run for you, right? Then once you have set the proper analysis that you intend to do, then click OK. Also, you may want to, let's say, write solutions to the file itself and so on, right? So once you run it, then you should get your answer, okay, or the result. Okay, so the idea is that you can see the software will have the meshing part and the solutions part. Okay, these are the different type of analysis that the software may do for you, right? And these are actually obtained from the Lisa manual, right? So if you so if you just open up the Lisa menu, right? So you will have this manual with you. Okay, this is a very important first step. Okay, you just download this one. Okay, just follow the tutorial how to create mesh. Okay, mesh, create the refining. Okay, forming the CAD model, then run the analysis, right? Our intention is to run the static, so you just follow the static, right? Then from there onwards, you select or define your material, assign your load, and you run your results. Okay, this is the display, right? So inside the menu itself, they will tells you what type of element they can solve, okay, using like for this static 3D. Okay, for this static 3D, the menu will specify that for this static 3D cases, they will only accept solid element, okay, or shell element or beam element or truss element with this particular elements ID, right? Then what type of load and constraint they support, these are the things. So sometimes if you assign it wrongly, then the software may tells you it cannot run, right? So you have to check whether the element is correct or the load applied is correct for that particular analysis, right? 2D is different, 3D is different, right? So 2D, you can see that they only support plane and so on, okay? So if you have meshed it with a 3D elements, the software will prompt you that they cannot solve, right? So this is how you should able to identify where is the problem, right? Then for the axis symmetry, you also see that they can only solve using this element. If you select different type of element wrongly, even though you select axis symmetry analysis, it will not give you the answer, right? So selections of elements is important, okay, according to the analysis type. Okay, same thing with the thermal. You may have thermal steady state, transient for fluid, right? So that is the things, okay? So once you have set up everything, you just click this equals, okay? Then the software will start to solve for you, right? So once it's solved for you, then you get the result, okay? When it also shows that during solutions, okay, they will tells you how long it takes, okay? For luckily the model that I draw previously, okay, is very simple. It started at 5 p.m. okay, it takes 1 second to finish, right? So what happened is that behind the software, they assemble the matrix, they apply the constraint, they solve the matrix and find the reaction force and get the answer, okay? So it's actually doing the what we have mentioned previously, the steps, okay? All this software using the same concept of finite elements, okay? This is what happening behind it, right? Once they get the answer, now all this answer or values is still a value, so we need another features of the software to display it, okay? So that would become to the interpretations of the software, right? So the software will need to post-process them, right? Reinterpret the results, okay, into stress, strains, and other results, okay? So this is the displacement results that we can see, right? So in this model, I think I set this as a fixed regions, maybe I forgot, right? I fix this to a fixed region, then I apply some loads, right? So you can see that there is a displacement across the object or the model itself, right? And the software will display in this way, okay, by color coding them, okay? We call this as post-processing. The software now interpret all those value into colors, right? The problem is that what is the unit for this displacement, right? This is where your unit system is very important. If you initially use mmgs unit system, then for sure this displacement will have a unit of millimeter. All right, if you are using a unit system of SI, everything you define is in meter, then your result will be in meter. All right, so to kickstart, all right, so you have your first assignment, okay, very simple assignment, okay, just download the software, draw any models you like, okay, very simple straight line models, whatever it is, okay, run a simple static problem, model it, run the static, and get the displacement and one miss stress result. Okay, very simple. Okay, draw any cube that you like, put any boundary condition that you want, put any loads you want, run the analysis, and that's it. You can submit, right? So when you submit, you just put like define your problem, put your model, okay, then show these two results, displacement and what's Mr. stress with the unit, right? So it's only 4 marks, okay, for this assignments, just to make sure that you know how to use it. All right, either you don't submit, or if you run successfully your analysis with proper description of unit at the end of your, let's say you have to tell me what is the unit, okay, of your result of the displacement, what is the maximum displacement, maximum stress, okay, let's say, okay, then you get 4 marks, okay, 0 to 4, right? So remember, this is just assignment number 1. You have the assignment for this course is 20%, right? So this one give you 4 marks of it, okay, or 4% of it, right? Very straightforward assignment, right? To give you an idea of how to start, right? Okay, so moving onwards, right? So the assignment part, I don't care on the detail, right? As long as you get the result as it is, you interpret it, that's it, right? So now come to the more other considerations, okay, when we use the finite element models, okay. So far, any questions before we proceed? Maybe a few more slides here. If you have questions, you can keep posting the questions, all right, so we will answer it later on, right? So on the modeling of your finite element models, okay, there are several considerations that you may have to take note, right? You must be aware of, okay? So the results would be as accurate as is, but with a certain knowledge of it, okay? So you may want to use a rough estimate, okay, to just cross-check, okay, whether it is reasonable or not, reasonably true or not, right? If it is too far away, meaning something is wrong with your model, okay, either your model is wrong or the units that you put in is wrong, right, and so on, right? So that all these boundary conditions like loads, units, and etc., right, is still under the so-called the development of your finite element model, right? So when we come to a meshing, okay, meshing of your model itself, if you are meshing with a very large element, okay, if you are meshing with a very large element, then you can see that there is a big area which it is not counted, okay, in your calculations, okay. Whereas if you are using a smaller elements, okay, then this area that being neglected is smaller, right? This is where you may want to use a finer mesh, right? But at the cost of computational time, right? So more mesh or more elements involved, okay, when we call mesh, okay, so mesh means you break them into parts, right, discretize them, meaning to say you have more elements. Let's say this is a shell type of element, so you have 1, 2, 3 elements, okay, meaning to say you may basically have maybe 6 or 7 or 9 equations to solve simultaneously. But then if you have 1, 2, 3, 4, 5 and so on, then the number of equations involved that you need to solve simultaneously behind the computer is getting larger and larger, right? Then the time for it to get the the converged solutions is longer, right? So what you need to do is you may want to fine tune it, right, to see to take a balance between them. Okay, sometimes if you see that there is a little changes in between this area, you may just assign it with a larger elements, whereas when it is become more critical, large changes, okay, very big slope of curve over here, then you may want to have more refined mesh over this area. Okay, this is how you can fine tune to find the balance between getting the right amount of mesh, okay, when you solve for your problem. Okay, so that would develop through experience from time to time, right? So for now, you just make it run, that's it. Okay, then slowly you can play around with all this refinement slowly. Okay, then next would be the wrong choice of elements. Okay, for example, if you are using a plate-like geometry, okay, like a wall, okay, but then the thickness is very thin, okay, then for sure you can either use shell elements or a quadratic solid elements. Okay, but then if the beams are too thick or the membranes are too thick for a plane stress, okay, these terms you will come across in one of the chapter later on. Okay, we will define that later on. Okay, or too thin for a plane strain, okay, another set of problem, right? Then the selections of the elements would be very important, right? Then also we have this so-called linear elements as well as the quadratic elements. Okay, so for a linear elements itself, this is connected with a very straight line. Okay, whereas in between them, this is quadratic element where you have a mid side node in between them. Okay, this allows these functions to take a quadratic. Okay, this one can go down and up, right? So to form a quadratic line itself, right? So this will give you a different type of functions, okay, behind the equations, as well as the accuracy of the solutions that you get later on. Okay, another things that you may want to consider is whether your mesh consists of severely distorted element or not. Okay, generally or ideally we would want, let's say, a triangle elements. Okay, we may want to have a triangle with equal length, okay, equal lengths of all these three sides, right? But then for sure when we do auto mesh, okay, at certain angle and so on, okay, we have no choice but these ideal elements get distorted. Okay, sometimes you may have a part where it have this form, okay, very thin. Okay, then we call this as a bad shape element. Okay, and bad shape elements will reduce the accuracy. All right, so therefore the elements that being assigned across or mesh across your models is important. Okay, so again, another keywords that you may come across later on in the concept of finite elements is this isoparametric. Okay, in the Lisa FEA software itself, all the elements are defined using a isoparametric equations or coordinate system, right? You may come across this later on. Okay, so you can see that in the finite elements analysis software itself, you can see all these terms appear, and when you go through these courses, you will understand why or how they will affect, okay, your selections of equations. Okay, so these are several elements that I would say distorted. Okay, the first one is we try to avoid a large aspect ratio. We call aspect ratio when we compare the length and the breadth. Okay, the length and the breadth itself, okay, we just divide them. Okay, we call it as aspect ratio. If it is higher than 3, then it's not recommended. Okay, it's not recommended. Okay, but still, if you can't avoid it, then yeah, just go ahead, right? But we just take note on all this small part. All right. Then also highly scale. Okay, if it is more than 30 degree, okay, scale, then it's again not recommended. Okay, if it is a quadrilateral element with 4 nodes, okay, but then when it somehow readjusts itself, okay, then it will looks like a triangle, okay, like this one, almost like a triangle, and this one is a triangle, then again this is not recommended. Okay, when you have this quadratic element, okay, but then there is one side which is strongly curved, okay, this part suddenly curved too much, then again not recommended. And the last one is when it is a quadratic elements, but then one of the node is too much off center, okay, again this is not recommended, right? Not recommended means try to avoid, but then if it is not avoidable, then maybe it is only affect a few elements, then it's okay if that element or the locations of the element is not located at the critical region. Okay, also you may want to see there is a mesh discontinuity. Even the software itself, sometimes they make some error and so on. Okay, so that mesh discontinuity may occurs like this. Okay, we may want to mix and match two different type of elements together, and you will found that this triangle itself, then there is a mid node, okay, in between them, and this one is a linear type of elements. Okay, you cannot allow the software to connect the mid node with the normal nodes, okay, of the element. Okay, so try not to do this, okay, at all, okay, because it will generate an error. Okay, the software will not able to solve the equations, okay, associated with this situations. Okay, then also you may want to generate like an element with a gradual transitions, okay, from a coarse mesh, okay, to a finer mesh. Okay, so we're trying to not using very coarse mesh, then suddenly there is a very fine mesh. Okay, try to take a transitional, okay, slowly reduce, okay, that will give you a better results. Okay, I would say others considerations like this one, okay, same thing, okay, similar to this. Okay, you may have a triangle with 6 nodes, okay, but then this one of this is connected to the midsole. Okay, don't do that, right? Same thing, even though there is a mid node, okay, that try not to use the edge, okay, the edge node, okay, connect with the mid node. Okay, again, edge node, okay, connect to the mid node, right? So don't do that, right? And the last one would be there is a mix of these two triangle. Okay, even though it looks a triangle, but then this is a 3-node triangle, 1 node, 2 node, and 3 node, right? Whereas this is a 6-node triangle, 1, 2, 3 with 3 mid node on the side. Okay, so they are two different type of elements. Okay, two different type of element, and what happen is that sometimes you may not notice this additional node, and what happen is that when you run the analysis, they may have this so-called a gap opening, okay, or maybe this one penetrate to another element, right? Because this point can move up or down, okay, meaning to say you can see this coming down or up, right? Whereas this 3-node triangle, they must form a straight line, right? So therefore they may have this problem in between your mesh, right? So this is where the auto-generated mesh, they generate by the computer, but then sometimes error occurs, okay, because of some algorithm problem. Then you have to identify where is this problem occurs. Okay, they may come in this particular form. Okay. Then also on the limitations of the software, okay, you may take note that for Lisa FEA, they can only model a linear portions of a stress strain curve. Okay, meaning to say you have a stress strain curve, right? Okay, Lisa only model on this part, okay, which obeys the Hooke's law, okay, or Hooke's law model, right? The rest, it may not able to model correctly, okay, because the equations associated with this software itself only limited to the linear portions of the stress strain curve. Okay, so that is the limitations of this software. Okay, other software they may have other limitations and so on. Okay, so this is where you need to understand slowly, all right, what happens inside the software. Okay, sometimes they generate the solutions. Okay, it looks like okay, but then when you do a testing or when you compare it with your experiment, then you notice there is a problem. Okay, like if let's say you want to model a fracture mechanics, okay, you use Lisa FEA, okay, you try to do a tensile testing, okay, you pull until it start to yield, okay, then slowly fracture. Okay, the problem is that if you do that, okay, for the initial part it will be the model will be correct, okay, but then during when it start to yield, okay, when it start to come to this particular point, then the analysis actually give you a wrong answer. That's why no matter how you adjust your analysis result and the experimental result may not match. Okay, this is where the software may have some limitation, okay, within different type of software, right? So you have to understand the material models behind it. Okay, besides it's important you constrain your model properly, okay, put in proper deformations or maybe fixed support, roller support, or whatever it is, okay, and also the others like translations or rotations of your model, right? So I think that's concludes this whole FEA software. So hopefully by throughout this 1 hour sessions, you able to, how would I say, understand what actually occurs in the FEA software. Okay, and slowly, okay, in the next few chapters, okay, you start to go into the equations behind all the formations of all these elements from a beam elements to bar and so on. We move on from line elements, okay, the beam elements means the line elements, and we slowly move on, right? So that's all from me for today's. Okay, so hopes it gives you some ideas of what is running behind the software, okay, so that you aware that all this finite element software will give you results, but that result doesn't mean it's always correct. Okay, so that's all from me. So if you have any questions, so let me know. If no, then we will end these sessions and we'll come to the next sessions again. Any questions so far? Let's check. No questions, no question for now. Okay. Okay, so if no questions, we will end these sessions for today and see you on the next sessions again. All right, so don't forget the assignments. Okay, just download the software, follow some examples, run it, display the result, and that's it, right? Okay, so see you for now. Thank you. Bye bye.